Hi everyone. Today we are going to discuss one more concept here, power factor. Yeah, it's a concept in terms of utilization of electrical energy subject. What's that power factor? It's nothing but it's just an cosine angle of voltage and current. Just observe the things. Actually, you're having some inductive loads and capacitive loads right now. Actually, you're having some 95% or all the loads are inductive loads only there. It is represented with the letter L. Another loads is also there, capacitive loads. See, yeah, just remember one formula for the sake of one phasor diagram. Civil. Just observe first three letters CIV and the last three letters VIL. Just consider VIL like this. VIL. L stands for inductor. In a pure inductor, voltage leads current by an angle of 90 degrees. Or else we can write tact like this. Current lags voltage by an angle of 90 degrees. That's why all the inductive loads are lagging loads right now. Remember that line? All the inductive loads are which type of loads here right now? Lagging loads. Whereas for the part of capacitive loads, CIV now, in a pure capacitor, current leads voltage by an angle of 90 degrees. That's why these type of loads are nothing but leading loads. Yeah, remember that thing. But we are having some 95% of loads are inductive loads only there. Those loads are nothing but lagging loads. Yeah. It's just power factor is nothing but it's just a cosine angle in between the things of which two things, voltage and current. And we all know that lagging and leading loads right now. Just observe one more thing here. Lagging loads in the lines, just try to go for reference of voltage. Lagging here is we are having some current component like this, lagging. By an angle of how much here right now? 5. Yeah. Draw some two components here for this current. One of the component here is vertical component and this one is nothing but horizontal component, right? This component maybe call it as cos term, I cos phi. Another component here is I sin phi. Yeah, this one is a phasor diagram. Just I took one voltage as reference. It's a lagging loads now. Current lags by an angle of how much here? Phi. And I just want to produce two current components, I cos phi, I sin phi. That's it. Observe this diagram. This one is the thing. I cos phi, I sin phi. I cos phi in phase with the part of which thing voltage. I sin phi 90 degrees out of phase of voltage. From that, I just want to go for one triangle here. The triangle maybe call it as power triangle. Yeah, just multiply with the help of I cos phi with voltage. Same voltage V sin phi. And this one is VL. We are having some VI sin phi, VI cos phi, VI. Three types of powers we can evaluate here. VI cos phi is nothing but it's a type of power here as active power P. VI sin phi is nothing but it's a type of power here as reactive power Q. And this one is nothing but total power S. Three types of powers here. Just remember the name. We are having some three types of powers. VI cos phi, VI sin phi, VI. This type of power may be called it as active power P. This one may be called it as reactive power Q, and this one may be called it as total power S. From that, can you evaluate what's the value of cos phi here? It's a ratio of P by S. This one is a formula. You have to remember P by S. And don't neglect, you are having some units here as for the part of active power, kilowatts. For the part of reactive power here is kilovolt ampere reactive. This one is kilovolt amperes is the unit. That's it. Yeah. The total power or apparent power S is equal to it's a combination of P plus JQ. Yeah. If there is active power is increasing means it's the best option. There is some slight Q is enough there. If the reactive power increases means there is some reduction in the part of which thing active power. Yeah, it's a dangerous and as a result that power factor will reduces. That's the main drawback of having this. If there is any increase in the reactive power, there is a drop in the part of which type of power? Active power. Then there is some reduction in the part of power factor cos phi. Yeah, these are the basic lines. This one is the thing. They can have some formula like this: cos phi is equal to kilowatt by kVA or else P by S. Don't neglect this formula. Cos phi is equal to P by S. P units are kilowatts, S unit are kilovolt ampere. That's it. Yeah. We are having one more triangle, impedance triangle, same triangle here. What I have drawn, that it is nothing but like this. Yeah. This one is perpendicular and this one is phi. This one is R and this one is Z and this one is X. From that, what's the value of Z here right now? R plus Jx. From the triangle, what's the value of cos phi there? Cos phi is equal to adjacent side R divided by Z. This one is the formula they have written. Yeah. Just for the sake of what's this triangle name, maybe call it as? It's obviously Z stands for impedance. This triangle maybe call it as impedance triangle. Yeah. Finally, just try to understand one thing here. I just want to draw one triangle right now. This one is phi, and this one is P, and this one is Q, and this one is S. Yeah. And we are having some, this Q is nothing but units of kilovolt ampere reactive, kilowatts kVA. From that, can you evaluate what's the value of cos phi? That it is kilowatt by kVA. Or else, what's the value of power here? VI cos phi. Yeah. From that, can you evaluate what's the value of I? It's obviously P divided by cos phi. Remember that current and the power factor is inversely related. And this cos phi is inversely related to the part of S. Remember these two lines. These are the, if the value of cos phi is low, there is some increase in the part of which thing? kVA from this equation. The value of cos phi is low, there is some increase in the part of which thing? Current. These are the different disadvantages of having this low power factor. Yeah, just observe the right one formula P equal to VL IL cos phi. From that, what's the value of IL? P by this one. Yeah, from that, another formula here is cos phi is inversely related to which thing here? kVA. If it is low of cos phi value, there is some increase in the part of which thing? kVA. That it is larger kVA rating of equipment is required if you are having some low power factor. That's the first and foremost thing. And obviously, we have to bring some to transmit some fixed amount of power at constant voltage. If there is an increase in the current, that current is inversely related to cos phi now. If there is any increase in the current, we have to use some conductor sizes as large as possible. That it is one more drawback. Yeah. If there is some increase in the current, there is some copper losses also high. I square R is nothing but copper losses. I square R losses increases. Poor voltage regulation. What's that voltage regulation is nothing but sending end and receiving end voltage. You have to maintain some sending end voltage and receiving end voltage is as close as possible. If there is any drop in the receiving end voltage, we have some poor voltage regulation due to the part of which thing low power factor. Finally, by handling this every equipment, if you are having some low power factor means there is some reduction in the part of reduced handling capacity is also possible. All these are different disadvantages of low power factor. Remember this thing. Only two formulas, cos phi is inversely related to kVA, current is inversely related to power factor. Yeah. What are the different causes of power factor, low power factor here is all the equipments what you are using, that it is AC motors or of which type here? Induction type. They cause some low power factor. And we are also having some arc lamps, electric discharge lamps, industrial heating furnaces. All these work under low power factor. The load on the power system is also varying. That it is also one more criterion for having some low power factor. Remember, all the induction type motors are having some low power factor. Lamps, discharge lamps, heating furnaces, everything. What you have covered, all the values will have some cos phi is low. Yeah. Actually, in order to have this particular one, remember only one line here. Let it be you are having some source and you are having some load. All the loads are which type of loads here? Lagging loads. Lagging in the sense cos phi is low. Let it be I have to send some current here I to the load IL. But these loads are lagging loads now. Cos phi is as low as possible. In order to compensate this particular one, I would like to insert one equipment here in order to improve that power factor by placing some power factor improvement devices here. Right now, observe this one. What are the different power factor improvement devices here? Is these are the devices: static capacitors, or else synchronous condensers, or else phase advancers. All these are different power factor improvement devices. Yeah, this one is a source. We can supply some current I and it receives towards the part of IL. But these type of loads are cos phi is lagging. In order to improve this to the leading section, I would like to place some capacitors like this in delta connection for three phase supply, inserting in parallel. Then it can give some which type of loads here, it becomes leading right now. And the resultant, we can improve that power factor by placing some which thing capacitors, or else synchronous condensers, or else phase advancers. Just observe one thing here for the sake of understanding phasor diagram like this. Just observe here. We are having some source and we are having some load. I just want to place one motor here, synchronous motor. Let it be this one is synchronous motor. Yeah, that synchronous motor here is it draws some current here as IM. I just want to place this one in order to improve power factor. Just observe what's the current here I, load current IL, but I would like to insert one thing now, motor current is here as IM. Just take that reference as voltage V. It's a lagging loads now. What's the current here? IL. Having a angle of how much? Phi L. But my intention is I would like to improve that power factor. Power factor improvement is nothing but, can you remember what's the value of cos 30? It's approximately 0.866. If I'd like to reduce this angle to 0, what's the value of cos 0? 1. Then the power factor will improve if the angle is reduces. That's only intention. Yeah. I just want to place this green colored one will carry some current IL. But which type of load it is? Leading. Current leads voltage by an angle of 90 degrees. IM is perpendicular to which thing? Voltage. I just want to join IM and IL by using some parallelogram law. Draw some parallel line to the green line like this and draw some parallel line to the part of this red colored one and join these two things with the help of some current I. I is equal to what's the formula? It's a combination of IM plus IL. And can you observe one thing? This phi L is reduced to the angle of this blue colored one. It's as slow as possible. Phi. Then we can improve this power factor with the help of placing some static capacitors, or else synchronous condensers, or else synchronous motors. All these are used in order to improve the part of which thing? Power factor. Yeah, this one is the thing. Yeah, remember this phasor diagram. Simple phasor diagram. Yeah, just observe one more thing here. We are having some most economical power factor. Yeah, just observe one thing here. Most economical power factor in the sense, my intention is actually you're having some loads here, having some lagging loads now. In order to improve this one, I just want to place one capacitor in parallel. That it is in order to improve this power factor. My intention. But while going for the part of what's that most economical in the sense, let it be the bill for the part of initial condition here is 500 rupees. But when I can place some capacitor, the bill reduces to 400 rupees only right now. How much is the savings right now? 100. But you have to consider one more thing here. How we can reduce this bill to 100 rupees right now here is by placing one capacitor. But please consider the charge on this particular capacitor also. The charge on this installing this capacitor may be 150 rupees there, just 50 rupees. What's the net saving right now? Only 50 rupees is the final saving. Consider that one also here for the part of annual or net saving right now. Yeah, we can save how much here right now? Only 50. Only one thing, initially we are having some few 500 bill, but we can reduce to 400 by placing one capacitor. Consider that capacitor rate also there in order to go for the savings. The capacitor rate is 50, remove that one also. Final saving here is only 50 rupees. That one is the thing. That's the annual saving. This one is the thing they have given right now. For that, observe this diagram. Actually, this one is the diagram what we have drawn initially for triangle. This one is P and this one is Q. Q units are kVAR and this one is S. Two triangles I have drawn. If I'd like to reduce this particular Q value, there is some improvement in the part of which thing power factor cos phi. Only one simple line. If there is any reduction in the Q value, there is some improvement in the part of which thing cos phi. Observe the first triangle O A B. We are having some kVR1 there, and the value is kVA1 P. Yeah. If I'd like to improve from B to C, the kVR will reduce, and obviously there is some improvement in the part of power factor. Phi 1 is reduce the things to phi 2. There is some reduction in the angle, and obviously there is some improvement in the power factor. That's the only lines. What's the formula for cos phi? Cos phi is equal to P by S. Yeah, remember that thing. Or else, can you write like this? Observe this slide. Yeah, this one is the same slide here. From that, what's the value here is only some simple derivation. kVA maximum demand at cos phi. kVA1 is equal to, what's the formula there? Just write, just remember, cos phi 1 is equal to P by, what's the formula here? kVA1. Yeah, from that, what's the value of kVA1 is equal to P divided by cos phi 1. 1 upon cos phi 1 is equal to P secant phi 1. Same for the part of kVA maximum demand at cos phi 2. kVA2 is equal to P upon cos phi 2. It's a P secant phi 2. Annual saving in maximum demand charges here is it's S now. S units or kVA. That's the only thing we did. Maximum demand. Charges now make it some X. I don't know this X charges. How many rupees I have to invest for this maximum demand charges here is X. That it is kVA1 minus kVA2. What's the value of kVA1? P secant phi 1 minus P secant phi 2. This one is the first equation for the part of annual savings in terms of maximum demand. Same for the part of Q. From this triangle only, what's the value of tan phi here? Anyone? What's the value of tan phi 1 is equal to? It's obviously kVR1 opposite divided by P. From that, can you write what's the value of kVR1 from the above triangle? It's obviously P into tan phi 1. That's the thing they have written. It's a reactive power in terms of reactive power units or kVR1. kVR2 is equal to P tan phi. Leading kVR taken power factor correction. It's the difference here, right? Phi 1 minus phi 2. Annual cost means nothing but let it be that one is y. I don't know that y value. Yeah, Py tan phi 1 minus phi 2. Observe, this one is the total power S and this one is the reactive power. What's the savings here is net annual saving is equal to subtract equation 1 from this one. That it is S minus Q. That it is saving. That it is annual saving. We get some equation maybe like this. This one is S. S is nothing but net annual saving is equal to maximum demand S minus Q. We get some equation maybe like this. X into P secant minus this one. In order to have this maximum value or economical value, just differentiate this one with respect to changing quantity here as phi 2 and equity to 0 in order to get which one? Maximum or economical condition. And try to differentiate this one with respect to phi 2 here as xp secant phi 1 minus this one, there is no phi 2, that's why it becomes 0. With respect to p secant phi 2 is equal to into tan phi 2. And is there anything here? No, it also becomes 0. This first term and this third term becomes 0. What's the value of differentiation with respect to tan phi 2 is secant square phi 2. From that, I just want to evaluate the things here as tan phi 2 is equal to y by x secant phi 2. Finally, sin phi 2 is equal to y upon x. Most economical condition here is cos square. Sin square plus cos square is equal to 1 now. From that sin square plus cos square is equal to 1. From that, what's the value of cos square is equal to square root of 1 minus sin square. I know the value of sin square here is y by x. This one is the most economical power factor condition. That's the only thing you have to write here. That's it. I just want to use only two things here. Can you remember the two things here? Only one thing. From this triangle, what's the value of cos phi? It's obviously P by kVA. Right? That kVA1 is equal to, what's the formula? P by cos is nothing but P secant phi. Same for the part of second triangle. This one is kVA. Same thing, try to write tan phi 1 is equal to kVR in terms of reactive power divided by which thing here? P. From that, can you write kVR1 is equal to P tan phi? What's the next condition here? From these equations, subtract this one from this one. We get some S value. And then what's the next condition there? Go for the part of differentiation with respect to phi 2 and equate it to 0 to get maximum condition there. And we can have some final power factor cos phi is equal to 1 minus y by x square under root. This one is the most economical power factor condition. Yeah. Yeah. Thank you for watching you. If you like my video, please subscribe to my channel. Thank you.